This is Engineering 246, Lecture 3. Today we're going to talk about Chapter 3, which is torsion. But before we get into that, let me just recap a little for you all the things that we've talked about up to here. So we started off in the first lecture just introducing the concept of stress. And we talked a little bit about the two types of stress, right? Normal stresses and shear stresses. And then we talked a little bit about factors of safety and the idea of an allowable stress. In Chapter 2, we talked more about axial stresses, right, meaning stresses that put a part in tension or compression, and then we related that to axial strains, and we started talking about Hooke's law, the generalized Hooke's law, and looking at composite rods that were in tension or compression. We also introduced the concept of a shear strain, and then the idea of a general state of stress. Okay, so we're going to talk now about torsion. Okay? And torsion is just another pure way of loading a structure or loading a simple part. Okay, so this is the second way that we're going to look at of loading a part. The first way was simply to put a part in tension or compression, right? And we kind of showed the equations that related to that, and okay, let me draw for you what I meant. So if I had a regular circular rod, we talked about pulling it in tension or compression, and the equations that are relevant here, you might recall, are stress is going to be force P divided by cross-sectional area A. Okay. Strain is equal to the deformation or elongation divided by the original length. Then we had Hooke's law that related normal stress and normal strain. And then if you combine all these three, you could get a expression for the total deformation, which depends on the force applied, the length, the area, and Young's modulus. Okay? And this is probably the simplest way that we have of loading a simple structure. Right? It's simply to pull on it, to elongate it, or to push on it, to compress it. The method of loading on the part that we're going to talk about today is referred to as torsion. And torsion is basically applying a torque to a shaft. Okay, so now I'm going to have the same circular structure, but instead of pulling or pushing on it, I'm going to twist on it. Okay, so you can apply equal and opposite torques. Okay, and this will twist on it, of course. And this is very different from pulling the structure in tension or compression. Okay, so let me give you some points about terminology. There are different terms that we use to refer to these structures, okay, depending on what kind of load they're subjected to. When we have something that's subjected to just pure tension or compression, we call that a rod. Okay, so a rod is something you pull in tension or compression. When we have something that we're going to twist on, we refer to it as a shaft. Geometrically, they could be completely identical. Right? We're talking about two circular structures here, and basically, depending on whether you pull it in tension or compression or whether you apply a torsion to it, it's referred to as either a rod or a shaft. In the next chapter, we're going to load it yet in a different way. Right? We're going to load it with transverse loads, which are loads that are perpendicular to the long axis. Okay? So if I load it transversely like so, now we refer to it as a beam. Okay? And then if I stand this structure vertically and compress it, now we refer to that as a column. So these are just different terms that are used, okay, depending on the types of loads that are applied. Okay, so get used to these terms. All right, so going back to this idea of torsion. Okay, the most important thing when we talk about torsion probably is the fact that torsion usually applies only to circular shafts. Okay. You could certainly apply torsion to a non-circular shaft, right? So for instance, I could take something that's rectangular and twist on it. Okay. But what happens to this shaft is very different from what happens to the circular shaft when I twist on it. Okay. And there's a very compelling reason for that, which we'll get into. Okay. So that has to do with these two images on the bottom here. Okay. You can see on the top image, right? This is what happens when you twist on a circular shaft, and then on the bottom is what happens when you twist on a rectangular shaft. What you can see is that the circular shaft does not warp. Okay? I look at every single cross-section on that shaft, and each cross-section remains circular even after I twist on it. In the rectangular shaft, it's pretty obvious that the cross-sections are no longer rectangular. The whole shaft, you can see, warps. Okay? And the very fact that it warps means that stresses and strains are going to be distributed in a very complicated manner throughout this shaft, okay? And that makes it very difficult to analyze. And then you can see with the sharp corners, okay, those actually become points of very high stresses, or those are what we refer to as stress concentrations, as you might recall from the last lecture. Okay, so these are very complicated shafts, right? Non-circular shafts. So we will not be looking at these, okay? And that is actually not that big a deal out in the real world, because if you think of all the different shafts that you've seen out in the real world, and they're used all over the place, right? We have shafts connecting motors to any kind of tool that the motors are driving. You have shafts in pretty much every car, right? You have transmission shafts, axles, drive shafts, so on and so forth, right? So shafts are used all over the place. And if you think of all the shafts that you might have seen, okay, pretty much all of them are circular. And the reason for that has to do with what we just talked about, right? Circular shafts are just very well defined. They don't have any stress concentrations, and it's very easy to determine what the stresses are, right? So it makes the design process much simpler, okay? So we don't have to worry at all about non-circular shafts. All right, so when it comes to shafts and putting a torsion or applying a torque to the shaft, right? Again, all we're talking about is twisting on the shaft. And there are basically a couple of ways you can look at twisting on a shaft. All right, so let me explain to you all the different ways that you might encounter where a shaft is going to be twisted. I could have a shaft that is fixed at one end. Okay, so that's the left end in this case. And then it has a free end that I'm going to apply a torque to. So that's one way, right? And this is actually the same as the case where I have a shaft that's free on both ends, and then I just grab both ends and twist in opposite directions. The reason for that, of course, right, is equilibrium. In the top case, right, this is a fixed support on the left. The whole shaft must be in equilibrium. So if I apply a torque on that right-hand side, that support is actually exerting an equal and opposite torque. Okay, so that's actually, these two cases are actually equivalent. Right? These are static equilibrium cases. And most of mechanics of materials does deal with static equilibrium. Right? But when it comes to shafts, there are actually situations where we have objects that are not in static equilibrium. Okay, because I already mentioned you could have shafts that are hooked up to motors, right, that are part of the axle in your car and so on and so forth. So those shafts are obviously not in static equilibrium, right? Those shafts are rotating. However, the methods that we're going to talk about here actually apply to all cases of shaft equilibrium. It doesn't have to be static equilibrium. It could be dynamic equilibrium. Okay? And dynamic equilibrium simply means that the shaft is rotating at a constant rotational speed, right? It's got a constant angular velocity, if you will. So usually, in machinery, when you're talking about cars, the units we use are revolutions per minute, right? RPMs. So as long as the shaft is rotating at a constant RPM, then it's in dynamic equilibrium. And dynamic equilibrium and static equilibrium are actually the same thing. Okay? It means there are no accelerations. If there are no accelerations, then there are no net forces. And no net forces means what? Means sum of all forces, or in our case, right, sum of all moments, or sum of all torques is equal to 0, right? Which we do have in these two cases, and which you will have if you've got a case of a shaft that's rotating at a constant velocity. Okay, so that's just something to be aware of, right? Because you're going to run into some problems where you're going to see that some shaft is rotating at a given speed. And don't let that throw you off, okay? It doesn't mean that equilibrium doesn't apply. All right, so let's go back to the slides here. Okay. What we want to do as far as a shaft under torsion is we want to come up with a bunch of equations just like we did for a rod that was under tension or compression. Okay, so we have to first determine what kind of a stress and what kind of a strain results when a shaft is put in torsion, right? And this figure kind of gives you an idea. If you look at this circular shaft here, okay, this circular shaft, the way it's drawn here gives you an idea. So what we do is we start off with our shaft, okay, before we apply a torque, and then down the side, you're just going to draw a very fine grid of squares. And using squares is basically the best way of determining whether, or trying to determine what sort of stress and strain your structure is going to be under. Okay, so you draw this grid of squares, and then you go ahead and apply your torque. Then you look at your squares, and you ask yourself how those squares deform, right? So remember from last time how we described normal and shear stresses, right? Under a normal stress, those squares just elongate into rectangles, or they get shorter, they get compressed into rectangles, right? But under a shear stress, you might remember that right angles become acute or obtuse, okay? So angles change. Squares become sort of diamond-shaped when there's a shear stress, okay? So if you go ahead and apply a torque on this shaft, what happens to that grid? What happens to all the squares that make up the grid? Right? I think it's pretty obvious that you can see all the squares lose their right angles, okay? So when you apply torsion to a circular shaft, okay, you get a shear stress. And if you get a shear stress, if you remember from Hooke's law, right, in both tension, compression, and Hooke's law and shear, a shear stress results in a shear strain, right? Just like a normal stress results in a normal strain. So that's the first thing that's critical as far as trying to derive equations, okay, that describe a shaft under torsion. Okay, we need equations for shear stress. We need an equation then for shear strain, and then we're going to apply Hooke's law and shear, and then somehow combine all those three equations to come up with an equation for the total deformation of this shaft. Okay, so let me draw an analogy for you between what happens in the shaft under torsion and what happens to the rod under tension compression. So here's the rod, right? Here, let me make two columns. One for the rod in tension compression, one for the shaft that's going to be under torsion or under shear. Okay? The stress here for the rod was sigma, or a normal stress, is equal to P over A. For the shaft, we have a shear stress. I need tau is equal to something, right? And we'll get to that. Going back to the rod, we have shear strain, epsilon, is equal to deformation over length. Okay. For the shaft, we need a, so epsilon was a normal strain. For the shaft, we need gamma, which is a shear strain. Okay. We need an equation for that. For the rod, we had Hooke's law in axial loading, right, which is sigma is equal to E epsilon. For the shaft, it's just the shear version of Hooke's law, right? So that's tau is equal to G gamma, if you recall. Right? Then we combined the three equations for the rod to get delta is equal to PL over AE. For the shaft, we need to come up with an equation, okay, that comes about from combining the three equations up on top. That's going to give us deformation. So how do we define the deformation in the shaft? Okay, so let's see if we could work that out. When you have a shaft that's in torsion, okay, there are two very important angles here. So here's what we're going to do. We take the shaft again, right, before we apply any torsion to it, and rather than marking it with a bunch of squares, well, all we do is we draw two lines. I draw a line right down the side, lengthwise, and then I draw a line that represents the radius. Okay? And then I go ahead and apply my torque. Let's say I applied this torque that way. Okay? And we'll get into this more, but usually when you talk about torques to shafts, we just apply the right-hand rule when we talk about positive and negative torques. Okay? So this will be a positive torque. If you wrap the fingers of your right hand in the direction of the rotation, right, your thumb points towards the right. That's the positive x direction. So this is going to be a positive torque, T. All right, so anyway, now imagine how these two lines are going to move or to deform, right? If I'm twisting that right hand down, and let's just say that this left end is fixed, then this long line, okay, since the left end is fixed, the left end of this line stays at that same spot that I'm marking with the dot, but then the rest of the line kind of deflects down. Okay, everybody see that? And then this radius deflects down as well. Okay, so I've got two important angles, okay, that are going to represent what happens to this shaft when it deforms. There's this angle here and that angle here. Okay, everybody see the difference between the two angles? Right. Let me mark this one in blue, actually. And then the other one, I'm going to mark in green. Okay, so the blue angle, All right, let's take a look at that first. What does that blue angle represent? Okay, so it's actually very easy once you realize exactly what that angle corresponds to. I'm going to draw back in that grid, okay? The grid of squares that we had, or imagine that you draw back in that grid of squares, right? If we look at just one of the squares, here is the square before it deformed, before we apply the torque. What happens to that square after we apply the torque? Remember, this was its bottom edge. This is now its bottom edge. Okay, that square deforms into that shape. Hopefully everybody can see that, right? So what is this angle? This angle corresponds to the change in the right angle of that square. And what do we define that as? That change in angle, right, to the square last time. We defined that, if you remember, as the shear strain. Okay, the shear strain is simply the change in the right angle of the square after it gets deformed due to a shear stress. Okay, so this angle here is actually gamma. That's our shear strain. Okay, the other angle, okay, we're just going to refer to as phi, Greek letter phi. Okay, and if you think about that, that represents how much actual deformation I have in this shaft. Because the larger the deformation, the larger that angle phi. Okay, so phi is what we call an angle of twist. And the angle of twist is simply what we use to represent the total deformation of a shaft. Okay, so what we need are equations for gamma and phi. And they're just going to come about from geometry. Okay, so rather than boring you with the details, okay, the derivation is actually really simple. If you take a look at this slide, on to the next slide, okay, it will show you exactly how to come up with the equations. But needless to say, okay, rho phi over L. Let me go back to my table here. Okay, this is rho phi over L, where rho is the radius of the cross section. Okay, now the radius, okay, can vary. The radius of the cross section varies from 0 at the middle of that cross section all the way to the outer surface of this shaft. Okay, the radius corresponding to the outer surface, which we're going to denote as C. Okay, so what that means is that your shear strain varies. Your shear strain varies from 0 at the center of the shaft, down the midline of that shaft, and it starts increasing, okay, and you can see that it's linear. It's going to increase linearly until it reaches a maximum at the outer surface of a shaft. So when you apply torsion to a shaft, maximum strains, and then, of course, that means maximum stresses occur on the surface of that shaft. And that should be something that's intuitive, because if you've ever seen a shaft that starts to crack, right, because there was too much load, too much torque applied to it, where does it start to crack? It cracks on the surface, okay, because that's where stresses and strains are largest. Okay, so that's our equation for phi. And then the equation for shear stress on the shaft, okay, comes about from another derivation, okay, that continues on from here. This one is a little more difficult, okay, so I'm going to skip that derivation as well. You can look at it if you're interested in the details. I don't hold you to to knowing the derivations. Okay, they're good to know, right, to kind of get a more full understanding of where these equations are coming from, but they're not necessary. Okay, all you really want to be able to do is to apply these equations. These are very fundamental equations that you don't really need to be able to derive on your own. Okay, so this is the equation in the red boxes for the shear stress. Okay, the derivation actually involves equilibrium. Okay, static equilibrium derivations, equations of equilibrium. Okay, so don't worry too much about the derivation. Okay, what's really important is that you know how to apply these equations. So because the shear strain goes from 0 at the center of the cross section to a maximum at the outer surface, then the same thing happens with your shear stress. Okay, it's 0 at the center of the circle going to a maximum at the outer surface. Okay, and when rho is equal to rho, meaning your diameter, your radius, right, is equal to its max, we just use letter C, lowercase c. So lowercase c, okay, you'll want to remember this, lowercase c is the maximum radius of your cross section, which means all the way to the outer surface. Okay? All right, so what is J in this equation? Let me just write that here. This is torque, okay, rho over J. So T is the amount of torque you're applying, right? And torque, just to remind everyone, is nothing more than a moment, right? It's a special kind of moment if you think back to statics. So it's a moment, which means it's force times distance, right? Newton meters or foot pounds, pound feet. Rho is the radius. And then J, okay, it's the polar moment of inertia. You might recall from statics what a polar moment of inertia is. Okay. So hopefully this is just going to be a review. From statics, you know that there are two types of moments of inertia when it comes to 2D areas. Okay. There's the regular moment of inertia. Okay, let me erase this slide. There's the regular moment of inertia I. Right? So if I have something called Ix, let's say, of this area, and this is the x-axis, then if you recall, I represents basically the resistance of trying to rotate this area about the x-axis. Okay? J, or the polar moment of inertia of a circle, okay, would be the resistance that you get when you try to rotate this circle about the axis that passes perpendicular to the surface. So if I made this the x-axis and that the y-axis, then the polar moment is the resistance that I get when I rotate the circle about the z-axis. Okay? So that should make sense to you, because when you twist on a shaft and you look at how a cross-section, the cross-sectional circle of the shaft moves or how it deforms, right? What happens to a cross-section when you twist on that shaft? It rotates about the long axis of that shaft, right? So, which is the z-axis according to my figure here. So when you twist on the shaft, okay, every cross-section rotates about this z-axis. So we'll talk more about that in a second. All right. Now, if you go ahead and combine these three equations, you're going to end up with the equation for deformation now, which is phi, which is going to be TL over JG. Okay? Torque times length divided by the polar moment of inertia multiplied by the shear modulus. All right, so what is the analogy between these two sets of equations? Right? The normal stress strain equations for the rod and the shear stress strain equations for the shaft. So here's how I want you to look at this. Okay, let's start with stress. For the rod, P is the load. So stress is a function of load. And then area is the resistance to that load. That's how I want you to look at this. Why is area the resistance to an axial load? Right. So when you have resistance to a load, what that means is if I have a large resistance, okay, for a given load, then that means the stress remains small. I'm able to resist that load by maintaining a small stress, because once you start losing resistance to that load and the stress starts going up, then it starts to approach the ultimate stress value, which means your part can break, right? So how do I resist a load? I resist a load by maintaining strength in my structure. And by maintaining strength, that means you keep your stresses as far away from that ultimate value as you can. Okay? So a large area provides a lot of resistance to that load P. Right? For a given P, if I have a large area, the stress stays small. For that same P, if I have a small area, that stress is big. Right? So if I take two rods, one has a very large area, one has a very small area, and I apply the same force to both rods, which one has more resistance to that load? It's the larger rod, right? Because the stress is going to be much smaller in the larger rod compared to the smaller rod. Okay? So stress is a function of load and of resistance. When it comes to axial stresses or tension compression, remember we said that the force is spread evenly over the cross-sectional area, right? So the stress is the same anywhere on the cross-section. Now, if you go to the equation for the shaft, okay, it's now a shear stress, but we should be able to maintain a pattern, meaning the shear stress in the shaft should be a function of load and resistance as well. Okay? So what is your load for the shaft? It's torque, right? The amount of torque you apply, right, is directly related to how much stress you're going to get. It's the load that you're applying. What is the resistance? Well, we just said that when you twist on a shaft, right, the cross-sectional area rotates, and the resistance to that rotation is your polar moment of inertia. That's J. So there's your resistance. Unlike the rod, right, that stress is not constant over the cross-section. We just said earlier that the stress goes from 0 at the center of that cross-section all the way to a maximum value at the outer edge, right? So that's just what rho does for you. Rho, right, is the term that governs how your stress varies from the center all the way to the outer edge. Okay? So there's another equation that's sometimes written here, and that's just and that's usually how shear stress is calculated in the shaft, right? We're usually interested in the maximum shear stresses, because the maximum is what's going to cause failure if failure were to occur. So what we usually use, right, we don't use the general tau equation, we use a tau max equation, and that's equal to Tc. Remember, C is the maximum radius over J. Okay, so there's the equation for stress. All right, let's go to the strain equation. For the rod, strain is a function of deformation, right, and length. Okay? So if you go to the equation for the shaft, what did we say was representative of the total deformation in the shaft? It's this value phi, right, our angle of twist, and there's length. And of course, just like with stress, we need this term for rho, right, radius, because our strain is also going to vary from 0 at the center to a maximum value at the outer edge. All right, then of course we have Hooke's law. No need to discuss those. And then you combine the three equations to get your total deformation equations. And just for the heck of it, let's compare the two deformation equations. Our deformations are functions of load, that's P and T, function of length, right, the two L values, function of resistance, that's area and polar moment of inertia, and then function of material, right? As far as material properties go, we're going to use Young's modulus for tension compression and the shear modulus for shear. All right, so we have an analogous set of equations for the shaft compared to the rod. Okay, so get very comfortable with these two sets of equations because these are basically the only equations you need when you're talking about rods in tension compression and shafts in torsion. Okay, so let's move on. So once you have these equations, okay, now I want to take a detour, if you will. I talked just now about two very important ways of loading a part, right? Loading a structure. And one is to put it in tension compression, and the other is put it in torsion. Okay? But those are pure loads. Okay? And it's very tempting to say that when you put a rod in tension or compression, you're going to get normal stresses and normal strains, and you get nothing else. Right? And it's very tempting to say when you take a shaft and apply torsion to it, you're going to get purely shear stresses and shear strains and nothing else. Okay? Again, it's very tempting to say that, but that is not true. Okay? What I want to get across to you is this idea that stresses and strains are actually a matter of perspective. They're a matter of how you define your coordinate axes. Now, in the case of a rod and a shaft, it's pretty obvious how you should define your coordinate axes, right? If I have this rod, and now let's make it rectangular, okay, that I'm applying tension or compression to, it makes perfect sense to just align my coordinate axes such that one of my coordinate axes, let's say the x-axis, coincides with the axial direction or the long axis of the rod. And then the other two directions can be y and z. Right. Same thing when you have a shaft that's in torsion. If I have this shaft that's in torsion, okay, it makes sense to line up my x-axis with the long axis of this rod again, right? And then the other two axes are going to be y and z. If I define my axes like this, right, for these two cases, then yes, in terms of x, y, and z, I do get purely normal stresses and strains in the first case, and I get purely shear stresses and strains in the second case. Okay, so let's take a look at the rod first. What that means, okay, if I define my coordinate axes by x, y, z for tension or compression, okay, is that when I look at how this rod is going to deform, I want to draw a square. Remember, we represent points by by either a cube, right, in 3D, or by a square in 2D. The equivalent of a cube in 3D is a square in 2D. And in a case like this, you only need to look at the surface, right? So I'm going to look at what happens to a square that's on the surface of this rod. And since I define my x, y, and z axes like so, that square has to line up with those x, y, z axes, right? And now you can imagine what happens to the square once you apply that tension. It stretches, right, into a rectangle. And you can see there are no changes in angle. All the right angles stay right. So you get purely sigma and epsilon, right? You get normal stresses and normal strains. But that's just because I define my coordinate axes in that way. Okay, let's change things around. What if I change my coordinate axes? Maybe my x-axis is now in this direction, x, and that's y. Z still comes out of the board, comes out of the page, right? Now what happens? In order to look at the stresses in these new x, y, and z directions, I need to draw my square to match up with those coordinate axes. So I draw my square like this, right? And now when I pull on this rod, how does that square deform? It might stretch a little bit, right? But it's also going to get distorted into some kind of a diamond shape. Right angles are no longer right. So if right angles are no longer right, is there some shear stress that goes on here? The answer is yes, right? So you can see that it's a matter of perspective, and it's a matter of how you define your coordinate axes. When I have this rod that's in pure tension and compression, if I don't line up my coordinate axes with the axial direction, then I will get some shear stresses and shear strains. Okay. So how do you kind of try and understand why this happens? So let me draw an analogy for you again. It doesn't matter how you define your coordinate axes, really. Okay, the stress that you get from one set of coordinate axes should be equivalent to the stresses you get by using a different set of coordinate axes. Okay, the values are going to be different, but they equate to the same state of stress, as we call it, right? Remember we had this idea of a general state of stress. So my analogy has to do with forces, and we'll keep this in 2D just to make it easy to visualize, right? But obviously this extends to 3D as well. Let's say I have a force, okay, in 2D space. I've got some force. And I've got two force gauges that are set 90 degrees apart. They measure forces in two directions, one in that direction, one in that direction, let's say. Okay? If this force is applied to that point, and I apply or I attach my force gauges to that point, let's say I lined up the force gauges so that one gauge is in that direction and one gauge happens to coincide with that force F. What does gauge 1, let me call that G1, right? What does gauge 1 measure? Zero force. What does gauge 2 measure? It measures a force equal to that force that I apply, right? Why? So this would be like the case where I have the rod in tension and I just set my x-axis along the axial direction or along the direction of that force, right? Because now what are my shear stresses? 0. The only stress I get is sigma x, right? However, now in this force example, right, what if I were to go ahead and attach my force gauges in a different way? Let's just do vertical horizontal, right? Now I attach my force gauges so that one is that way and one is that way. What force is this horizontal gauge going to measure? It's going to measure the x component of that force. The y the other gauge is going to measure the y component of that force, right? So now, gauge 1 measures F. Let's say I know this angle theta. It's going to measure F sine theta. For gauge 2, it's going to measure F cosine theta. So notice, right, in the first case, G1 was 0, G2 was F. In this case, G1 is F sine theta, G2 is F cosine theta. Are these two cases measuring the same force? Of course, right? They're both measuring that force F. And in fact, right, if I take the square root of the sum of the squares in both cases, what am I going to end up with? I end up with that magnitude of force F, right? So just because I attach these force gauges in two different ways, I'm going to get two different readings from those force gauges, two sets of different readings. But even though those two sets of readings are different, they represent that same force. Okay? So it's the same thing when it comes to stresses. When I have this rod under tension, it makes sense to set up my coordinate axes such that the square is just lined up with the direction of the force, right? And then all I have is a normal stress. There are no shear stresses. But if I happen to set up my coordinate axes a little differently, then I might end up with both a tension and a shear stress, right? I end up with both normal stresses and shear stresses. Okay? So it's a matter of perspective, but when you have something very simple like a rod in tension, then you're just going to set up your axes to match up with the direction of the force. Okay? And in fact, right, the reason you would do that, right, if you actually need another reason, is that the stress that you measured when everything is lined up correctly, it's going to be the largest stress. This stress that you measure, right, this normal stress that you measured, it's much larger than the normal stress that you would measure if you were using a different set of coordinate axes. Right? And remember, we're always interested in the absolute largest stresses in the parts we look at, because the absolute largest stresses are what's going to indicate if your part is actually getting close to the ultimate stress value or getting close to failing or breaking. Okay? All right, so now let's move on to torsion. In torsion, okay, the same thing applies. I could either set up my axes to line up with the part, right, with the long axis, or I could rotate my axes. So something very interesting happens, okay, in torsion. If you set up your axes, coordinate axes, to line up with the long axis, that would be like drawing the square on the left of this figure. Right? That would be drawing that. And we already said that if you twist on the shaft, that square deforms into a diamond. I get pure shear stress and shear strain when I line up my axes like that. But it can be shown that if you rotate your axes by 45 degrees, okay, like the square on the right, then that square actually just stretches. You get pure tension at 45 degrees. At a 45-degree angle from the long axis, you have pure tension. Even though you're twisting on this rod, okay, at 45 degrees, you get pure tension. That is quite an interesting result, okay? And the way we prove it is to look at a brittle material, a brittle shaft. So here's a very important property about something that's brittle. So I'm talking about brittle materials will be like concrete, right? A piece of chalk, okay? Glass, any type of a ceramic, right? Those are all brittle materials, meaning they snap very easily. Not very easily, but very suddenly. Okay? Well, here's another very important property about brittle materials. A brittle material, okay, is usually very strong in compression. It's pretty strong in torsion, but it is extremely, extremely weak in tension. Right? That's why a column of concrete, you would never try to put concrete in tension. Right? Concrete is used to support bridges where they're only in compression. Right? If there's any possibility of the concrete actually going into tension, then you wouldn't use pure concrete. You would start embedding steel rods inside that concrete, right? What we call rebar. And that's because steel is very strong in tension. Right? So if you take something that's very brittle, right, a shaft that's very brittle, and you twist on it, okay, here is something that we know. The ultimate stress and torsion of something that's very brittle is greater than the ultimate strength of that material in tension. Okay, so what I mean by that then, right, in terms of symbols, is for a brittle material, tau ultimate is greater than sigma ultimate in tension. Okay, so let's imagine what's going to happen. I take this shaft that's made out of a brittle material and I start twisting on it. I grip both ends and I start twisting on it. Right? In the vertical direction, up and down, we know it's in pure torsion. Okay, so, and then at 45 degrees, we know it's in tension. Okay, so at 45 degrees, okay, that tensile stress is going to reach its ultimate value before the shear reaches its ultimate value. So how is a piece of brittle material, like a piece of chalk, right, when you twist on it, how is it going to break? Well, it breaks at 45 degrees because at 45 degrees is the direction of tension. Okay, and it is very weak in tension. So if you have a circular shaft that breaks at 45 degrees, what does that break look like? You draw a 45-degree line all the way around your shaft, what do you get? You get a spiral, right? So in the next slide, here, the top figure is a shaft, a brittle shaft that's been twisted until it broke. You can see that there's a 45-degree spiral break, a spiral fracture. Okay. On the bottom is a shaft that's ductile, meaning it's very strong in tension, very weak or much weaker in shear. In that case, we know shearing happens at, just at the regular vertical horizontal direction. So you can see the clean vertical break in the ductile material on the bottom. Okay. The demonstration that's always done, right, if we were in the classroom, is I would take a piece of chalk and we would twist on that piece of chalk until it broke. And what you would see is it breaks at 45 degrees. You get that nice spiral fracture. Okay? So you could try it on your own if you have access to a piece of chalk, or if you remind me when we meet in person for the first time, right? Remind me about this demonstration, and we could go ahead and show it and prove it. All right, so related to this, let me just give you a kind of a side story that I always find very interesting, and I like sharing this story with students because it kind of shows you that mechanics of materials applies more to just bridges and buildings and things like that. Okay, so my PhD is in biomechanics, and when I was doing my research, I worked in a medical school, okay, working with bones, with human bones. So I worked with orthopedic surgeons, right, who operate a lot on people who break their bones, right? They're always fixing broken bones. And what they tell me, at least what one of these surgeons told me, was that during the winter months, especially during ski season, okay, the most common fractures that he fixes are spiral fractures in the long bones of people's legs. Okay? And you should now know exactly why that is. Okay? So bone has a lot of calcium in it. So bone is a very brittle material. Bone can actually shatter. Right? And what that means is bone behaves just like this material on the top figure here is, right? If you put bone, a piece of long bone under torsion, okay, it will break at 45 degrees because that's the direction of tension. And bone is going to break in tension much more easily than it breaks in shear. So the reason that these spiral fractures happen so often in skiers, I would imagine, since I don't ski, right, is that it's easy to catch your ski on the snow, right? Maybe as you're walking around or moving around, or even as you're skiing, right? It's very easy to catch the ski and then twist your leg. And if you twist your leg, you're obviously applying a pretty large torsion, a large torque to the long bones in your leg, and that causes them to break at this 45-degree angle. Okay? So I always thought that was very interesting, right? And, you know, bones are mechanical structures, okay? Mechanical structures do not have to be metallic. They don't have to be concrete, right? Or even plastic. They could be bone. They could be biological, right? And it's actually a very rich area, right? Biomechanics. Biomechanics is applying a lot of this stuff that we're learning now, this mechanics of materials, right, statics, even dynamics. It's applying all of these mechanical engineering type courses to biological structures. And what makes it so interesting and what makes it a little more difficult is that biological structures like bone are not as well defined as something like steel, right? Bones vary in size and shape from person to person. They will vary in strength. They could even vary in Young's modulus and Shear's modulus, right, from person to person. So there's a lot of variability in biology, right, which makes it a little more difficult to deal with than just, you know, materials that are very, very well defined, like metals. All right, so that's my little side story for the day. Okay, let's move on. So now that you have all these equations, okay, here's an example for you, and maybe we'll try and work this one through, or at least start working this one through. All right, so we have this shaft that has a bunch of pulleys on it, okay, and we're applying different torques to the shaft. Now, this shaft has to be in equilibrium, right? If it's not in equilibrium, then this is not something we could solve. Okay, so it is in equilibrium, and the way you could tell that is if you add up all those torques, the net torque should be 0, right? And you can see that everything does add up to 0. You know, use your right-hand rule again, right? So the first torque from the left, that's 6 kilonewton meters. That's a positive torque, right? A positive 6. The 14 is also a positive. Then the 26 will be a negative. And then the last 6 kilonewton meter on the right is also a positive. So you can see the 3 positives add up to 26, right? Which cancels out that negative 26 kilonewton meters. All right, anyway, all right, so they tell you that shaft BC is hollow. They give you the inside and outside diameters. AB and CD are solid, okay, with diameter D. So for the loading shown, find the minimum and maximum shearing stress in shaft BC. Now, I didn't talk yet about hollow shafts, right? But in the hollow shaft, right, If you're trying to find the shearing stress in a hollow shaft, and you look at the cross section, okay, you have two diameters. You have the inside, or two radii, I'm sorry. You have the inside radius and you have the outside radius, right? And since stress is T rho over J, if you don't like the use of this variable rho, right, Greek letter rho, just look at it as TR for radius over J. Okay, I don't think there's really a need to use rho. That R, lowercase r, is not used really for anything else in mechanics of materials. So you could use it for radius if you would like. Okay, and then your max radius, of course, is C. Anyway, right, if you look at that equation, where is your minimum stress going to be? Well, it can't be at rho equal to 0 because there's no material there, right? I mean, technically, it is 0 there, but there's no material there, so it's actually not part of the shaft. That hollow portion is not part of the shaft. So as far as where there is actually material, it's going to be on this on the inner radius. Okay, so that's where your minimum radius, your minimum stress occurs. And then your maximum stress obviously occurs on the outside again. Right? Now, what is the polar moment of inertia for a hollow shaft? Okay, so I didn't get into that before, but here are your moments of inertia, okay, for solid and hollow shafts. In a solid shaft, you can see up on top, okay, it's 1/2 pi times your outer radius to the 4th power. Okay. For a hollow shaft, it's very simple, right? You add up the moment of inertia of the solid outer piece, and subtract out the polar moment of inertia of that hollow piece, that inside piece. Okay, so if you want, it's 1/2 pi times the outer radius to the 4th minus the inner radius to the 4th. Okay, so let's go ahead and go back and try to solve the sample problem. All right. Okay, so let's look at part A. Find the minimum and maximum shearing stresses in shaft BC. That's this middle shaft. Okay, so it's hollow. They gave us the diameters, right? So all we need to apply is for BC, okay, tau minimum is T, let me do R sub I, that's R inside over J. Okay, so R inner is just 90 millimeters, 45 millimeters, half of the 90, right? So that's 0.045. So that's torque times 0.045 meters. And then J is 1/2 pi outside radius to the 4th, right? So that's 60 millimeters, 0.06 to the 4th, minus 0.045 to the 4th. Okay, so that's how you find tau minimum, and tau maximum is more or less the same, except you replace that 0.045 on the top by 0.060, all right? But what is the torque? How do I determine the internal torque in BC? Because remember what we said, right, in the previous lectures, is that stresses always come about from internal loads. They never depend on external loads, right? You never calculate them from external loads. You always calculate them from internal loads. So it's actually pretty simple, right? If you remember last lecture when we talked about tension compression of rods, we had problems that were actually very similar to this, right? We have rods that were made of different segments, and instead of having torques applied, we just had forces applied. Okay? And if you remember how we determined internal forces in those rods, right? I said you choose a reference, and then you start making cuts, and you start asking yourself, what is the force that you need at that cut, right, to maintain equilibrium? And whatever force that is will be the force, the internal force in that segment. So you do the same thing when it comes to torsion. Okay, so in a problem like this, I will go ahead and choose the left-hand side as my reference. Okay, so there's the left-hand side as my reference. And then if I wanted to find the internal torque in BC, I make a cut between B and C. So you can see that if you make that cut between B and C, what you have is you have 6 kilonewtons positive plus 14 kilonewtons positive. Right? So what do you need at that cut to maintain equilibrium? You need 20 kilonewton meters. So T is 20 kilonewton meters. Okay? Negative or just opposite in direction to that 6 kilonewton and 14 kilonewton meter. Okay? So just go ahead and plug in 20, and that's how you find the stresses in BC. All right? So that's part A. For part B, okay, part B is nice because it's now a design problem. Part A was a pure analysis problem. We knew the torques or the loads, right? Or at least we were able to figure out the torques, and then we knew all the dimensions, and we were just asked to find stresses. So when you're asked to find stresses, that's a pure analysis problem. That's just plugging in all the values that you know and finding a stress. Part B is a design problem. Part B says we actually want to design the diameter of D, the diameter D of shafts A, B, and C, D. Okay? And what they're going to give us is an allowable shearing stress. Remember what allowable shearing stress means, right? If you go back to your definition for a factor of safety, right? Factor of safety was equal to your sigma ultimate divided by sigma allowable, right? Well, when it comes to shear stresses, it's the same thing. Your factor of safety is your tau ultimate, your ultimate shear stress, divided by your allowable shear stress. So anytime you're given an allowable shear stress, or an allowable stress for that matter, what that means is a factor of safety has already been applied. So rather than using the ultimate stress, you are going to use that allowable stress. Okay? Another way of giving you a problem like this would be to give you a factor of safety, right? If you were given a factor of safety, then you go ahead and multiple and kind of take your ultimate stress and divide it by the factor of safety to end up with your allowable stress. And the allowable stress, of course, is the largest stress that you're going to be applying, or you're going to allow to be applied. Okay? So for part B, tau is now known, and tau is TC over J. Okay? Tau is now known. It's going to be 65 megapascals. Okay? So what are we solving for? We're solving for the radius. Okay? And A, B, and C, D are solid, which makes it a little easier. Okay? So let's go ahead and write out the equation that we'll be using. So, let's start with AB. Okay, it's hard for me to write on this slide, so it's much easier when I have a blank slide. Okay, so before I go to a blank slide, let's first determine the torques, internal torques. Right, the torque in AB should be pretty obvious, right? It's 6 kilonewton meters. torque in CD, if you look at it, it's actually also equal to 6, okay? So torque is 6 kilonewton meters, okay? Allowable stress is 65 megapascals. So here's how we're going to solve part B, okay? Tau is TC over J. That means 65 mega, remember, is 10 to the 6 pascals, is equal to 6 kilonewton meters. That's 6 times 10 to the 3rd newton meters. Okay, C is unknown now. C is the radius. I'm solving for the diameter, so what that means is I solve for C and multiply by 2. All right, and J, if you remember, is 1/2 pi C to the 4th for a solid shaft. Okay, so if you look at this, the only unknown that you have is C. So you're going to solve for C, okay, multiply by 2 to get the diameter for shaft AB and CD. Now, if you think about that, right, what can you say about that diameter that you get? Must you design this shaft to be that diameter? Must A, B, and CD be exactly that diameter that you solved for? Okay, so not necessarily, right? What the value means that you get for the diameter is if you use exactly that diameter for A, B, and CD, then A, B, and CD will have exactly 65 megapascals of stress. So you're going right up to the limit. What does that mean? It means that diameter that you solve for is the absolute smallest that you can make those shafts. If you made them any smaller, okay, the stress would exceed 65 megapascals. You will be going over what's allowed. Right? Can you make the shafts larger than the diameter you solve for? The answer is yes, right? If you made them larger, then what happens to the stress in those segments? Well, the stress is going to be less than 65 megapascals, okay? Now, the allowable stress only means that it's the largest stress that's allowed, okay? It's actually good, it's great if you could get smaller, right? If you go smaller than 65 megapascals, okay? When you sell a product to a customer, right, and you tell them what the allowable stress is, what you're telling them is do not exceed this stress, okay? It's, of course, great if you apply less than that amount of stress, but do not exceed the stress. All right, so that's a very quick illustration of how you use the stress equation. So the next part, okay, is going to be looking at angles of twist. Okay, and I probably don't need to spend a lot of time with these next couple of problems because they are very similar to the problems dealing with tension compression. Okay, when we dealt with problems with tension compression, okay, we had composite rods, as you recall, right? And then we were asked to find the deflection at the free end. Right? That was the first type of problem. We had something like this. Right? We had something like right, maybe a couple of segments fixed at one end. I applied a bunch of forces at different locations. All right, if you remember, we had a problem kind of like that. And then you basically had to find the total deflection at this free end, right, at that free end. Well, we can now change this problem just around a little bit, okay, where instead of applying forces, we're going to apply torques. So I might apply a torque here, a torque here, a torque there, right? And now, instead of finding the deflection at that free end, we're going to find the angle of twist at that free end. Okay. So the procedure is going to be exactly the same. What changes? It's the equations, right? Whereas before you did delta was the sum of PL over AE. Now we're going to have phi is the sum of TL over JG. That's the only difference. Okay, and a lot of times, okay, there is one more difference. Okay, phi, once you get phi, you keep in mind that it's going to be units of radians, which are dimensionless. So a lot of times what's expected is that you convert that total deflection into degrees. Okay, you're going to convert it to a rotation in degrees. But that's a very simple conversion, right? There are 2 pi radians per 360 degrees or pi radians per 180 degrees. Okay, so just go ahead and use that conversion. All right, so that's that. And then the other type of problem that we had when it dealt with rods was the statically indeterminate problems. Right? So if you remember, that would be putting a fixed support on both ends. Right? And then we talked about how you applied superpositioning to solve those types of problems. Same thing here. Okay? If you have a situation where where you have a problem like this, and this would be something you couldn't solve using statics, right? This now becomes a problem that you could solve using mechanics of materials. All right, so let's briefly discuss this problem. Let me redraw this a little better. Okay, so I've got 3 different rods, right? 3 different materials, and they're all kind of connected. They're all welded together, right? But then it's fixed. This whole composite rod is fixed at both ends, okay? And I want to find the reactions at both supports. And once I find the reactions, of course, then I could go back and find all the internal torques in each segment, and from the internal torques, of course, I could go ahead and find the shear stresses in each segment. Okay, so that's the kind of those are the kinds of things you could expect to be asked to find. All right, so let's go ahead and label this just like we did with the rods. That's A, B, C, D, E. Okay, and why don't we do this? Let's say AB is 6 inches. Let's use a US unit problem here, right? AB is 6 inches. Let's say it's got a shear modulus. Well, before we do shear modulus, let's give it a radius, right? So L, I need values for L. I need values for radius. Let's say it's 1 inch. Okay. And then I need a shear modulus. Why don't we say that it's 2 times 10 to the 6 psi. Okay, and then BC is also 6 inches, right? Radius of 1 inch, 2 times 10 to the 6 psi. CD maybe has a length of 4 inches, a radius of ½ an inch. G of 4 times 10 to the 6 psi. Right, and then DE has a length of, why don't we say, 5 inches, radius of 0.2 inch. G of 5 times 10 to the 6 psi. All right, are we missing anything else? Let's see. Oh, the applied torques, of course, right? So maybe this is 10 kip inches. This is, let's make it 20 kip inches. Okay, so how do you go ahead and solve this? The question then might be something like, find the reactions, right? And maybe find tau in each segment, tau max, meaning at the outer surface, right? In each segment. And then maybe find the angle of twist at some point, let's say point D. Okay, how would you solve this? So just like in the case of tension compression, you would go ahead and apply superpositioning, right? Remember what superpositioning says? It says you look at the effects of different types of loads separately. So what are the different types of loads that we have going on? One type, obviously, is going to be the applied loads, right? That 10 kip inch and the 20 kip inch. And then the other is simply going to be the supports, okay? So in order to look at the applied loads, you have to remove one of the supports, because the applied loads want to deform the shaft in some way, right? And what having both supports does is it prevents that. So in order to look at the full effect of what the applied torques are going to have, you have to remove one of the supports so that this shaft is allowed to deform freely, okay, based on the applied loads, okay? And then the second part is to look at the effect of the supports, right, the reactions exerted at those supports. So then you just put back in the torque that was applied by that support that you have removed in the first part. Okay, so let's break this up, right? First problem, the first part of the problem then is to simply look at the case where we have the applied torques. Okay, so I'm going to have to keep going back and forth here, right? 20 and 10 kip inches. (20 kip inches), 10 kip inches. This was A, B, C, D, E, right? So this is for the first part, meaning I keep my support on the left and I remove the support on the right, okay? So in order to, this is now statically determinate, so I can find the reaction, right? And that reaction, if you look at it, is going to be 10 kip inches, okay? Don't forget to apply the right-hand rule, right? So now what I'm going to do is I'm going to try and work out the deflection at E, okay, from part 1. Okay, so the deflection at E due to these applied torques is going to be the sum of TL over JG, okay? And this should be pretty obvious. Let's make a list for ourselves of internal torques, right? Torque in AB. That reaction is positive 10 kip inches. So if I make a cut between A and B, it's going to be a negative 10, right? Then the torque between B and C, I've got 10 and 10 positive, so I need a 20 negative. So minus 20, right? BC. And then CD is going to be the same. to negative 20. And then torque and dE, if you look at this closely, is 0, right? You don't need any torque. So I have 3 terms in this summation. This is going to be a negative 10 kip inches is 10 times 10 to the third, right? Pound inch. Length of AB, we said was 6 inches. J is 1/2 pi radius. What did we say radius was? I believe it was 1 inch, right? To the 4th. And then G we said was 2 times 10 to the 6 psi, I believe. All right, let's double check. Okay, yeah, 2 times 10 to the 6, right? 1 inch radius, 1 inch radius. All right. Oops. Okay, the next term is BC. That's going to be a minus again. 20 times 10 to the 6 times 6 inches. Right. 1/2 pi 1 to the 4th. 2 times 10 to the 6th. And then the third term is minus 20 times 10 to the 6th. Length was 4 inches, was it? Four inches, 1/2 inch radius, 4 10 to the 6 psi. Okay. 1/2 pi 0.5 to the 4th times 4 times 10 to the 6th. All right, so if you work this out, you're going to end up with some value. How about part 2? Part 2 says remove the applied loads. Okay, we're not looking at those now. We're going to look at the effect of the reaction. Okay, so if you're unsure what direction that reaction is going to be, and you don't even need to worry about that, right? You can go ahead and assume it's positive. Okay, so there's the reaction at E. It's going to be a torque in this problem instead of a force. Okay, and this is A. Forget about B, right? Then you have C, D. We don't have to worry about B anymore because there's no torque applied there anymore. Okay, so if you look at this is statically determinate, where the reaction at A is simply RE, negative. All right, so if the reaction at A is negative, and you make a cut at AC, and then CD and DE, then all your internal torques are positive RE. So the angle of, I think I made a mistake in that previous slide. Okay, instead of delta, what should I have used? Delta is a deflection, right? This is angle of twist, phi. Okay? So next, angle of twist at E in the second part is, again, sum of TL over JG. So now it's going to be RE, 12 inches, 1/2 pi, an inch to the 4th, times 2 times 10 to the 6 psi, plus RE times 4 inches over 1/2 pi 0.5 to the 4th, 4 times 10 to the 6th, right, plus RE, what was the length here? I think it was 5 inches. Go back. 5 inches, 0.2 inch radius, and then 5 10 to the 6 psi. Okay, so 1/2 pi 0.2 to the 4th, 5 times 10 to the 6th. All right, so this is going to give you some number times RE. Now, how are we going to go ahead and combine parts 1 and 2? Well, part 1 says E deflects by some amount if there was no support there. Right? Part 2 says there actually is a support there, and it's trying to twist it in the other direction by some amount. Okay? And what happens when you combine these together is you say phi at E from part 1 plus phi at E from part 2 have to add up to 0 because there's no actual deflection. And if you look at that equation, the only unknown is RE. Okay, so find RE. Once you have RE, what do? You do sum of torques has to be equal to 0. Right? What is that going to give you? That gives you RA. Once you have all of that, then you start making cuts, finding internal torques, right? And then using tau is equal to TC over J to find the stress at each segment. Okay, and then to find the phi at D, you do sum of TL over JG, where you now know the actual internal torques in all the segments from A all the way up to D. Okay, so that's how you work out that problem, and it's very similar to the case of a rod, right, of a composite rod under tension and compression. Okay, so let me move on from this. If there are any questions, okay, feel free to email me, or I should be back. I am hoping for the next lecture. Okay, hopefully I'll be back in the country, and we could, address any concerns that you might have at that time. Anything that I can't answer by email. Okay, so let's move on. Okay, angle of twist, statically indeterminate shafts. The next type of problem, and the last type of problem, actually, okay, has to do with gears. And gears are very important when it comes to shafts. Right? And by gears, I mean there are many different types of gears that are used. We're talking about the simplest types of gears, which are like the ones shown in this figure. Right? These are what we call spur gears. And spur gears have a couple of functions. Right? The simpler of the two functions is basically to just transmit rotary motion. Okay? Meaning, let me give you a scenario here. Maybe you have a motor. Okay, it's spinning, the motor is spinning. Okay, and you want to use that motor to drive a tool that's here. So you can see that the shaft in the tool, or the input in the tool, does not line up with the motor, right? The shaft of the motor. So one thing you can do is you attach a shaft to the motor, right? You have the shaft to the tool, and then you use gears. One gear on that shaft and one gear on this shaft, right? And now you're basically transmitting the rotational motion of that motor to the tool. Okay? So that's one function of these spur gears, right? It's to simply transmit rotary motion. And if I don't want to change the speed, right? Meaning if the motor is rotating at a certain RPM, and then I want the tool to rotate at that same RPM, I just use gears of the same size, right? They have the same number of teeth, if you will. However, okay, and this is the other function of gears. If the gears are of different size, okay, and they have different number of teeth, then I not simply transmit the rotary motion, I'm actually going to change the speed of rotation that I'm transmitting, and I could change the amount of torque that I am applying, okay, to that tool. So let me discuss that a little bit. When you have two gears that are in contact, right? If you kind of blow up what happens where they make contact, these gears have teeth, right? So let me draw that a little better. So that's one gear, right? This is the other gear. You can see that the teeth mesh with each other, right? So if this gear is turning, then the teeth on this gear basically push on the teeth of this other gear, causing that other gear to rotate, okay? So the whole idea is that at any moment, there's a single point of contact, okay? There's always a little bit of a gap, right? So there's always just one point of contact between the teeth on the gears. And Newton's third law basically says if the tooth on the left gear pushes with some force on the tooth on the right gear, then the tooth on the right gear is going to push back with an equal and opposite force. Okay? So what that means is the forces acting on both gears are the same. You have the same force acting on both gears. That's very important. Okay? So same force acting on both gears, and we're looking at the case now where the gears have different diameter or different radii. Okay, so if I have gear 1, and let's call gear 1 the input gear, meaning it's the one hooked up to the motor. It's driving the second gear, right? Gear 2, it's the driven gear. You have an input gear and you have a driven gear, right? Gear 1 has radius R1. Gear 2 has radius R2, okay? The force, okay, on gear 1 is F. The force on gear 2 is the same. It's equal to F, okay? Now, if I know that there's a certain torque that's being exerted by the motor, right? That means that there's a torque on gear 1. Okay? I want to find how much of that torque actually gets transmitted to gear 2. Okay? So how do I determine that? Well, what is torque? Torque is a force times a distance, or force times a moment arm, right? So in a gear, there's the force acting on the edge of the gear, right? There's the moment arm. The moment arm is nothing more than the radius. So what is the torque in the first gear? It is FR1, okay? The torque in the second gear is actually FR2. And we know that the F's are the same. Okay, so what can you do with this? If you solve for force in both equations, okay, and let me go ahead and erase some of this stuff. If you go ahead and solve for force, you get F equals T1 over R1. This gives you F equals T2 over R2. You equate the two, since the forces are the same, you get T1 over R1 is equal to T2 over R2. Remember, usually you know the torque in the input gear, so I know T1, I'm trying to find T2, so go ahead and solve for T2. T2 is equal to T1 right? Whoops, I miswrote this. This is R1. Right? So T2, okay, is T1 times R2 over R1. So if you have different radii in your gears, then the amount of torque that you transmit from the input gear to the driven gear is not going to be the same as simply the torque in the input gear, okay? What that means is if you vary the radii between the two gears, you could either increase the amount of torque that you're sending to the driven gear, or you could decrease the amount of torque that you're sending to the driven gear, okay? So one very good example of this, okay, is in the transmission of your car. Most cars have multiple gears in their transmission. Right? You start off with first gear, and then you shift, whether it's a manual or an automatic, right? Or these days, even with a continuously variable transmission, you basically just keep changing the size difference between your input and your driven gear. Okay, so let me illustrate that. Keeping in mind, right, let me write down that equation. T2 is equal to T1 times R2 over R1. Okay, so in most cars, your input gear is fixed. Okay, that's the gear that comes out of the engine. Right, that's hooked up directly to your engine, to your crankshaft. So there's your input. Okay? So there's the input in your car's transmission. First gear in most cars, okay, is a large gear. This is first gear. So why is that? Based on this equation that we have up on top, right? Your engine is putting out a certain amount of torque. That's T1, right? So that's from your engine. Okay? If your first gear, that's R2, right? Your input gear is R1. If R2 is much larger than R1, then what can you say about the torques? Then you can say that the torque when you're in first gear, right? So first gear basically is hooked up to your wheels, to your driven wheels, right? So the amount of torque that you're applying to first gear or the amount of torque that you're applying to your wheels is going to be much larger than the torque that's coming out of your engine. Does that benefit you in first gear? Right? Obviously it does. Otherwise, first gear wouldn't be designed in this way. So first gear is used, of course, when you're starting from a rest, right? And you have a lot to overcome when you start moving a car from rest. You've got to overcome all that mass, all that friction. So you need as much torque, right, or as much twisting power, as much twisting force as you could get. Right, you want to twist on those wheels with as much force as you could get to get that car moving, to get that car accelerating. Right, so you want first gear to be the gear where you could apply the most amount of torque to your wheels. Then as you shift up to second, third, fourth, and so on, the gear size gets smaller and smaller. Okay, eventually, once you get to your high gear is usually what we call an overdrive gear. And what that means is the gear size is smaller. And let's say this is 6 gear. A lot of cars have 6 speeds at least these days, right? So now 6 gear is much smaller than my input gear. And what does that mean? It means the torque that I'm applying to my wheels is actually now less than the torque that's being put out by the engine. Okay? And is that going to be a problem? It usually isn't, right? Because in 6 gear, you use your high gear once you've gotten up to speed, right? When you're moving on the highway at 55, 65 miles an hour, you would be in usually your highest gear, right? If you're cruising at any speed, you're in your highest gear. And how much torque, how much twist do you need on your wheels if you're already cruising at some speed? Well, you've got all this momentum, right? You barely need any torque really to get that to keep that car moving. Okay, so it's perfectly fine. Your high gear can be really small. You don't need a large amount of torque when you're in your high gear. And of course, if you're on the highway in your high gear and you want to pass someone, right? What do? If it's an automatic transmission car, you step on your gas and your computer basically downshifts for you. It goes down to a lower gear, right, where you have more torque available, and you need that torque to accelerate and pass the car in front of you. If it's a manual transmission car, what do? You just shift down 1 or 2 gears, right, sometimes even more, to a lower gear so you can get that extra torque to bypass the car in front of you. Okay, so that's torque. That's how you multiply torque and how you decrease torque, right, between the input and the driven gear. Now, there are repercussions to changing the gears, right, other than changing the torque. Okay, and most of you know that in a car, right, your top speed, the amount, how fast you can go in a particular gear, right, varies. It changes depending on what gear you're in. In first gear, right, you can't go very fast. You could be racing your engine. Your engine could be near its red line in first gear, and you might be moving at barely 15 miles an hour, right? Whereas in your top gear, that's usually where you could go, at the car's highest speed. Right? That's the gear you use to cruise at a really high speed on the highway. So the amount of engine speed the amount of speed that you get, okay, is going to be small, right, in first gear, and it starts to increase as you get higher and higher. So how does that work? Okay. So let's talk about that. So when 2 gears are in contact, here's your input gear. And let's use first gear again. Here is your driven gear. Well, the gears are meshing together, right? Their teeth are meshing together. So what that means is when your input gear turns by a certain amount, okay, means when it turns by a certain angle, your driven gear must turn by the same amount of linear distance, not by the same angle, right? Because your gears are in contact the whole time. They must be in contact over the same distance, if you will. What I mean by distance, okay, in the case of gears, is arc length. Okay, so the arc length in gear 1 must be equal to the arc length in gear 2. This is R1, right? This is R2. What is the equation for arc length? If you remember, right, in geometry, sometimes you use lowercase s, right? It's equal to r theta. So for input 1, it's R1 theta 1. Theta meaning the amount of angle that gear rotates by, right? And then that has to be the same for gear 2, so that's R2 theta 2. Okay? So now that we have this, let's take a look at rotations. So if gear 1, your input gear, rotates by some angle theta sub 1, right? Then we want to find out how much that driven gear is going to rotate by. That's theta sub 2. Okay, so you solve for theta sub 2, you get theta sub 2 is equal to R1 over R2 theta sub 1. Okay? So it's very similar to torque, but now it's opposite, right? Remember, in torque, it was T2 is equal to R2 over R1 times T1. For theta, it's the opposite. It's now R1 over R2 times theta 1. Okay? So what does that mean? It means, right, when R2 is much larger than R1, okay, then this ratio is small. And that means when gear 1, your input gear, rotates by a certain amount, gear 2 is going to rotate by a much smaller amount. Okay? Which is why in first gear in your car, you can't go very fast, right? Because your input gear might be rotating at, say, 6,000 RPM, but your wheels, or the gear 2, your driven gear, is rotating at a much smaller amount. Okay? In your high gear, gear 2 is now smaller than gear 1, your input gear, right? So your engine doesn't have to run very fast, okay, in order for your car to be moving at a very fast speed, because the amount that your driven gear is going to rotate by is much larger than the amount that your input gear rotates by. Okay, so that's the trade-off between torque and speed, right? If you want a lot of torque to be transmitted from your input gear to your driven gear, then the speed of your driven gear has to go down. If you want a large speed in your driven gear, then you can't have a large amount of torque. Okay, and that's all fine when it comes to a car's transmission, because those things actually, that's actually the way we want things, right? When we want a lot of torque, we don't need to go very fast. And when we want to go very fast, we actually don't need a lot of torque. Okay? All right, so that's how gears work. Okay? And all of this is going to be applied in the next type of problem. So we're looking at a problem just like this. Okay? You have two shafts that are connected together by gears. And in this particular example, you can see that shaft AB is the input shaft, okay? Meaning it's got a free end. End A is free. That's where I'm going to be applying some torque, okay? T sub 0. I'm going to apply some torque there, okay? And then that torque is going to get transmitted to shaft CD. In this example, D is fixed, okay? And then C is connected to end B of shaft AB, okay? And there are your two gears. You can see they differ quite a bit in size, okay? And then what you're asked to find, okay, is this. Part 1, find the largest torque that can be applied to the free end of shaft AB, okay? And then based on that amount of torque, find the angle through which end A is going to rotate. So a couple of things. The first thing is, you're going to look at this and you might say, well, this doesn't look like any type of a machine that I might design. Right? I don't understand what this actually does. So this might be something that's actually used in a torque wrench. Okay? So that's one thing. The other thing is, this doesn't have to actually represent something that you might design. Okay? This could be an approximation of a dynamic type of a situation. Right? So D does not necessarily have to be fixed. D could be driving some tool, and there's some resistance at D. Right? So keep in mind again that as long as, even if if these two shafts are rotating at a constant speed, right, that's very similar to a case like this where we have static equilibrium. Okay? You will work it out the exact same way. Okay? So don't worry too much about the practical application of this. Right? All right, so that's the first thing. The second thing is, you have to be able to take a look at this and tell me exactly what's going on with end A. okay? Meaning, when they ask for the angle through which end A rotates, you are not looking for just the deformation that exists in shaft AB, okay? So what I mean by that is this. Shaft AB, okay, is free at one end. The other end is hooked to gear C, and then C is part of shaft CD that's fixed at D. So try and visualize what happens when you start twisting on this end A, okay? If B were fixed, okay, if this was just one shaft where A was free and B was fixed, what would happen? B would not move at all, and then A would just start to deform, okay? And the way you will find how much end A rotates by is you just apply your angle of twist equation, right? It's TL over JG. However, is B fixed in this problem? It's not, right? B is hooked up to C. C is hooked up to D. So if you look at shaft CD, right, C actually is going to deform, and D is fixed, right? So if I wanted to find how much C is going to rotate by, then I can simply use TL over JG, okay? So that's the first thing, okay? You have to work your way backwards, essentially, right? You basically look at CD and say, okay, C is going to rotate, right, based on TL over JG. So I need to know how much torque is going to be applied to shaft CD, and then I use that torque to find how much C is going to rotate by. So C is going to rotate by some amount, and then B is hooked up to C, right? B is a smaller gear than C, so what do you expect to be the rotation of B? You, of course, from all that stuff we just discussed earlier with gears, right, you expect B to rotate by some amount that's greater than C. In fact, right, B is going to rotate by an amount that's larger by that ratio of 2.45 divided by 0.875, right? It's going to rotate by that ratio greater than C. So B rotates, okay? B is hooked up to A. So is A going to rotate by that amount? Answer is yes, right? So A will rotate by whatever amount B rotates by. But after B stops rotating, then how do you look at this? Well, after B stops rotating, you could look at it as if B is now fixed, okay? And if B is fixed, can I keep twisting on A? The answer is yes, right? Once B is fixed, I could keep twisting on A until it rotates by that amount, TL over JG. That amount is a deformation, right? When A just rotates along with B, right, there's no deformation in shaft AB. But then after B stops rotating, okay, then A starts to deform, okay, by that amount TL over JG. So the way we write this, okay, is this. We say that phi A, that's the amount that A is going to rotate by, is equal to phi B, that's the amount B rotates by, plus phi of A respect to B. We write that A slash B, okay? That means that's the amount that A rotates by once B has locked up. Okay, so let me rewrite that on a fresh page. We say phi at A is equal to phi at B plus phi of A respect to B. Now, what is phi of B? We said the amount that B rotates by depends on the amount that C rotates by, right? So if you remember, that's the ratio. That's RC over RB times phi C, right? And the amount that A rotates by with respect to B is simply torque in shaft AB, right? Length of AB over J of AB, G of AB. Because AB and CD can be completely different materials, different radii, different lengths, right? And so on and so forth. Okay? So how do I determine phi c? That's the amount that c is going to rotate by. That's going to be the torque in CD times the length of CD over J of CD, G of CD. Okay? And the only unknown here really is going to be the torque in CD. What is the torque in CD? Well, gear C is connected to gear B, and gear B is part of shaft AB, right? So basically, that's the amount of torque that gets transmitted from the first shaft to the second shaft. If you remember, that's going to be RB. I'm sorry, let me erase that. That's going to be RC over RB times the torque in AB. That's torque CD. Okay? Torque CD is equal to that. So this actually is equal to, notice you have RC over RB here, and you have RC over RB there. Right? So that's equal to RC over RB squared, torque in AB, length of CD, over J of CD, G of CD. Okay? So hopefully that makes sense. Okay, that's how you're going to get the overall rotation in A. So the overall rotation in A, again, is based on two things. It's based on how much B rotates by. Okay, there's no deformation there. A just rotates along with B, and then once C locks up, that means B locks up, and then A starts to deform. That's phi of A respect to B. All right, so let's go ahead and try and solve this problem. So in the first part, okay, they want to know the largest torque that can be applied to the end of shaft AB, right, given that the allowable shear stress is 8 KSI. So we're given an allowable shear stress, okay? So this is the same, both shafts are made out of the same material in this case. So that allowable shear stress applies to both shaft AB and shaft CD, okay? So let's go ahead and note that down. Okay, so let me go to the next page. We could erase this. Okay, tau allowable is 8 KSI. Okay, G was 11.2 times 10 to the 6, was it? PSI. Let me double check all of this. 11.2 10 to the 6 PSI, right, 8 KSI. The radius in shaft CD, let's not use R, okay, so because R is used for the radius of the gears, but the radius in shaft CD is 1 inch, the radius of AB is 0.75 inch, okay, so, oops. So C meaning the largest radius, right? C of CD is 1 inch. C of AB is 0.75 inch. Okay. Radii of the gears. Gear C, and we have gear B, right? These are 2.45 and 0.875. 2.45, 2.45 inch, 0.875 inch. Okay, then we have length of CD, length of AB. Okay, those are 36 inches and 24 inches. 36 inches, 24 inches. Okay, so the first part, part A, right? What is the allowable torque that I could apply? What is the largest torque that I could apply, right, to that end, that free end A, so that I don't exceed 8 KSI in either shaft? So think about how you're going to have to solve this, right? That 8 KSI limit has to apply to both shafts. So I might be able to find a torque, right, where one shaft goes right up to 8 KSI, but the other one exceeds 8 KSI. Am I allowed to apply that amount of torque then? The answer is no, right? Because now I can't exceed 8 KSI in either shaft. So what you need to do then, okay, is you have to solve for a torque that allows you to get all the way up to 8 KSI, okay, in both shafts. And then you choose the smaller torque. Okay? So let's go ahead and illustrate that. Okay? You start with shaft AB, right? You want to say tau in shaft AB is equal to T in shaft AB, C in AB, over J in AB, G. Right? There's only one G value. Okay? So we know tau. We're going right up to 8 KSI, so that's A times 10 to the third. It's equal to torque in AB. That's what we're solving for. Okay? C in AV is 0.75. Okay. J is 1/2 pi times 0.75 to the fourth. And G is 11.2 times 10 to the sixth. Okay, so solve for torque AB. You're going to get some value. Okay, I don't know if this example has been worked out in my slides. No, okay, it didn't get worked out in my slides. So I'm not going to spend the time to punch in these values and try and work it out, right? But you're going to get some value. Okay, and then you're going to do the same thing in CD. So you're going to say for shaft CD that tau in CD is equal to T in CD, C of CD over J of CD. Okay? And I made a mistake here in this previous slide. I'm sorry. Right, it's TC over J. There's no G. I don't need this G here. Okay, pardon me. All right, so for CD, okay, you're going to have 8 KSI, that's 8 times 10 to the third, is equal to torque in CD. C of CD is 1 inch. Right, J is 1/2 pi times 1 to the fourth. And you're going to get some torque CD. Okay? Now, I get some torque that I'm allowed to apply to CD and some torque that I'm allowed to apply to AB. But which is the more important value? Or can I just use that torque in CD as is? Okay? If you think about it, or if you look at what the problem is asking, they're asking for the largest torque that can be applied to the end of shaft AB. Okay? Meaning they're looking for the largest torque AB, not the largest torque CD. Okay? So how are the torques AB and the torque CD related? You know that because C and B are connected by those gears, right, that torque CD is actually RC over RB torque AB. Okay? It actually gets multiplied, right? The torque in going from B to C actually increases because you're going from a smaller gear to a larger gear. So what you're going to do is you're going to convert this to torque AB. Right? Meaning you're going to multiply by the ratio RB over RC and get torque AB. And now you can make a direct comparison between this torque here and the torque here. Okay? And which one are you going to choose? You will choose the smaller one. Okay? Because the smaller one will already have you going all the way up to 8 KSI in one of the shafts. If you choose the larger one, okay, then you're going to exceed 8 KSI in one of your shafts. Right? If you choose the smaller torque value, you will go up to 8 KSI in one of the shafts, and you will be less than 8 KSI on the other shaft. Okay, see how that works? By choosing the larger torque value, you will be at 8 KSI in one shaft, and you will exceed 8 KSI in the other shaft. All right, so once you have these torques, they ask you to find the angle of twist, or the amount of rotation in end A. Right? And that's where you go ahead and do this. You do this term plus this term, where you use that torque AB that you found in part A, right in here and in there. Okay? And that will give you an answer for the rotation at A in radians. So what you need to do is convert that to degrees. That's usually how you'll want to express an angle of rotation. Okay, so this is a gear problem. Okay, so make sure you understand this. This is a nice type of problem in that it illustrates quite a few different concepts. Okay, it forces you to understand how gears work. It applies stress equations, right? That shear stress equation. It also applies the angle of twist equation. Right? So there's a lot going on in these types of problems. Okay, so this is sort of an analysis problem, and it's sort of a design problem as well. Right? The analysis problem basically is in the second part, where you're asked to find how much A rotates by. Right? But the first part of this problem was actually a design problem, where you were trying to kind of come up with a design specification, right? Meaning you've already designed this system that you're trying to sell, and you need to come up with a value of torque, right? You want to tell your customer who you're selling this to, right? Do not exceed this amount of torque on the free end, right? Don't hook up a motor that has a torque rating greater than this amount. Okay, so that's a design problem. Now let me show you another variation of a design problem for this. Okay, and that would be if I just change this around a little bit. Right, let me go back to the problem here. So if I change this around a little bit, and I just gave you all of this, allowable stress, right, so on and so forth, and I don't give you the radii of the shafts, okay? I'm going to say shaft A, B, and C, D, I just want to make the same diameter, the same radius, right? But that's what I'm trying to find, and I want to design them in such a way that A maybe doesn't rotate by more than, let's say, 6 degrees. Okay, so now I have a specification that's dependent on how much A is allowed to rotate by. All right, and so let's keep the values that are given here. So we're going to retain the diameters of shafts A, B, and C, D, right? But now I'm going to ask you to find the torque at A such that such that A doesn't deform by more than 6 degrees. Okay? How would you solve that? Any ideas? All right, so if you go back to this, right, you're basically going to use this equation, except now you're going to be told what this value is. This is going to be 6 degrees, or convert that to radians, right? That's 6 degrees times pi radians per 180 degrees. And then you're going to say that's equal to these two terms added together. Okay? And what would be the only unknown in these two terms? It's the torque, right? Okay, so that would be another variation of the design problem, where you know what the maximum rotation you want to allow is, and you're going to solve for the torque that could be applied. Another very similar variation is what I started trying to show originally, right, which is the torque would be given, right, but the radii, or the diameter of the shafts, would not be. Okay, so now you're going to solve for the radii, or the diameter of the shafts. Okay. In that case, right, the T sub AB would be known. It would be the J value that you're trying to find. Okay. The J value, of course, is going to represent the radius of the shaft, and that, of course, is related to the diameter. All right, so this is one of the two probably most important types of problems out of this chapter. Okay, these gear problems and the statically indeterminate or the composite shaft problems. All right, I want you to be able to handle all these types of problems. Okay, so email me with any questions. Okay, and if you need to see more examples, there are resources out there, right? Look in a textbook. I posted a couple of solutions, right? There are solutions that are on Blackboard that you can make use of, or otherwise bring up your questions once I return. Okay, if you need to see more problems worked out in class on the board, then make sure you bring that up once I'm back in town and we have our first in-class meeting. All right, and hopefully that will be the next time we have a lecture. Okay, be on the lookout for notices. Okay, I will make an announcement either way, whether I need to do one more video lecture or whether we will be having class the next lecture. All right, so with that, let me end this lecture. The very next topic will be chapter 4. Okay, so we are moving along at a good pace, and I will speak with all of you again next time, whether via video or whether in person. All right, so let me sign off here.